All right, so I'm Gábor, and normally I work on natural language processing, probabilistic models, machine learning, and I don't even know how I ended up doing hash tables. A couple of people ask me. Sometimes they seemed interesting. Uh, so outline of this talk, I'm going to give you some motivation, for half of this talk, highlighting the performance differences between theory and practice. Then I'm going to give you the general idea of adaptive hashing and instantiate that idea on EQ hash tables and also on eco hash tables. Then I just wrap up. Okay, so motivation. Hash tables are everywhere, and they can take a substantial portion of the overall execution time. And even if they only take 2%, if you multiply that with Google scale, then we are talking about a huge number of CPU cycles. So it's worth thinking about how to improve these data structures to get better real-life performance. Now, I must say, this is Google CPU usage. The number is for a C++ code base, and this is this was done on SBCL just to make it fun for me. But the idea was a year ago to give the Google C++ guys a more convincing case, so they will build this. Okay, so what are hash tables? Just a quick recap. We have a universe of possible keys. We have actual keys in a hash table, which we feed one by one to a hash function, and that turns them into a single integer, and we take the low bits of that hash value and modulo the number of buckets. So the low bits, if it's a power of 2 hash table, and we put the key in the bucket that was so computed. Now, multiple keys might end up in the same bucket. That's what we call collisions, and we have some chain, maybe, conceptually, in the hash table. Right, so if we take the previous example and just count the number of keys in each bucket, we have the bucket count vector from which we can easily, with simple arithmetic, we can easily compute the expected number of comparisons we would need to do if we looked up a random key that exists already in the hash table. So this is a traditional cost model of hash tables, number of comparisons to be done for a lookup. Now, if this was not ideal, so if we only distributed the keys a bit more evenly in the hash table so that it's as flat, the distribution of bucket counts is as flat as possible, then we would get a perfect hash, and the cost would be minimal. We define regret as the difference between the actual cost and the minimum cost achievable, that is of the perfect hash. Now, in practice, most hash functions strive to be indistinguishable from a uniform hash given to us by theory. And a uniform hash is basically a function that assigns keys pretty much randomly with uniform probability to buckets. Now, theory has nice things to say about asymptotic behavior with such hash functions, but for this discussion, what matters is that uniform hash functions still have an expected non-zero regret, which is 0.5 at load factor 1. So there is a suboptimality that gets eaten by the big O cost that we look at in theory, which is not much. But if we can improve this and improve other factors such as cache friendliness and speed of the hash function at the same time, we might be able to gain something, right? So let's look at how it used to be. We compare SBCL's EQ hash, called prefuzz, and compare it with SBCL, where prefuzz is replaced by murmur. And you can think of murmur as pretty much a uniform hash. It's really good. So we feed as keys existing symbols in the running Lisp, and we plot the regret. The two lines are basically identical, and the wiggliness is due to the hash table storage being resized as keys are added. So on the x-axis, the number of keys. Regret is what is dictated by theory, basically. So they are identical. But the point of prefuzz is that it's a heuristic hand-designed function that is supposed to work really well for certain use cases. And you can see for the numbers on the next two graphs, or insertion, put, and the lookup, get performance, that prefuzz does indeed enjoy a small 10% advantage over murmur. And this is, in this case, there is not much structure in the key distribution. This is purely down to prefuzz being a simpler, faster to run hash function. So this is considered a reasonable gain, 10%. But if we take another example where keys are fixed nums, 1, 2, 3, basically, murmur behaves as it always does. But prefuzz starts out really strong, has almost zero regret for really small hash table sizes, starts to degenerate in terms of regret. More and more keys end up in the same bucket, and eventually it becomes pretty bad at large sizes. Now, if you look at insertion performance, prefuzz, surprisingly, it enjoys quite a performance advantage over murmur all over the range, even where it has worse regret. And that is because it has locality in its collisions. It's the subsequent keys end up in the same bucket, so it doesn't need to pay the memory access cost. Right? For get, the story is a bit different. It's still better than murmur, but less so because the benchmark looks up keys in random order, and the cache friendliness is not that not emphasized by that benchmark. Next example: single floats. Keys are single floats, also 1, 2, 3. I had to put the regret of prefuzz on the log scale just to be able to fit it on this graph. So what happens is that they only differ basically in the low bits, and prefuzz really sucks at using the high bits for reasons that we are going to see later on. And yeah, in this case, regret predicts real-life performance quite well. So we suffer a quadratic performance loss in the number of keys. So this is basically a denial of service right there. It's unusable. Okay, so we have general purpose hash function, murmur in this case, kind of. They are robust. They are designed to work with any key distribution, but they waste computation. So prefuzz did enjoy some advantage over murmur in some cases, and they have non-zero regret and do not care about the cache. They scatter everything in a most cache unfriendly way possible most of the time. Now, head-crafted hash functions can try to address these issues, but they become fragile in the process, and they fail badly outside the intended key distribution under the best circumstances. So we have something to combine. We want to marry the good things and drop the bad things. So Doug has talked about perfect hashing. We have offline algorithms, really expensive to do compute a perfect hash function for a given set of keys. So that's inspiration. We also have dynamic perfect hashing algorithms which can do this online. So as you would use a normal hash table, but they require a whole lot more memory. So they are not replacements, cannot be replacements for hash tables. So the adaptive hashing idea is that we want to change the hash function on the fly to given the keys that are added to the hash table without any change to the hash table API. And of course, it's a simple idea. Yeah, it's easier said than done. But the question is, can we do this fast enough? If we can, great. If we cannot, well, it was a good idea. So let's look at typical put implementation. Highlighted in red the new additions. So as put iterates over the keys in a bucket, we just count the number of keys, and if this number is too high, then we are going to fall back to a safer hash function and recompute the bucket. Now, if the hash table was full, we normally would double the hash table size and reallocate the storage. Now, and then do rehashing, which is like recomputing all the hashes, distributing the keys to the now larger vectors because the size has changed. Now we do some adaptation at rehash time because it's a convenient time to hide, amortize some of the adaptation cost that we see later. And if the hash function was changed, then once again we recompute the bucket and add the key value. So we have three mechanisms at a high level with which to trigger adaptation, exceeding a predefined limit on the bucket size, reaching a certain hash table size, and having too many collisions, more than would be expected with a random hash. And we can compute this easily, cheaply at rehash time when we need to iterate over the keys anyway. So how does this look for an EQ hash table? We start with a linear search like normal people do up until a certain size, and linear search in a vector. Now, the good thing about this is that it's faster, of course, for small sizes. More importantly, it does not need garbage collector support when keys are moved, because we are using the addresses, unlike so SBC actually uses most of the object addresses in EQ hashing. So if keys move, the GC has to tell user space basically to rehash. So when we exceed 32 keys, we switch to something called pointer shift, discussed later. And with pointer shift, if we encounter too many collisions at rehash time, or there are too many keys in the bucket, then we fall back on SBC as prefuzz, from which we fall back to murmur if need be. Now, pointer, approaching the meat of this, getting more detailed, the pointer shift hash function. So the basic idea is that we can actually construct the perfect hash for arithmetic sequences. If we can only detect the constant low bits of the keys. So if we detect that, we can basically remove the highest common divisor, that's a power of 2, of all the keys. Now it's EQ hashing. You can think of the keys as meshing words. So you divide it by the largest power of 2, that shifts out the common bits so that the low bits, constant low bits, get lost. And this is all that's needed for arithmetic progressions, keys forming arithmetic progressions to turn them into a perfect hash. So can we do this cheaply? I thought it would be easy, and I had multiple versions of this. What I ended up doing is extremely simple. Just as I showed at the bottom, just do 2 CPU instructions per key, 1 inclusive OR and 1 exclusive OR, followed by a single assembly instruction to count the number of zero bits in the mask that was computed. Details are unimportant. This is to demonstrate that it requires extreme patience and attention to detail to avoid the overhead, because we are doing the adaptation online. Now, what does this have to do with the cases that we care about? As we see as a page-based allocator, and it basically, when it doesn't run out of the page, it just bumps a pointer. And if we squint, the addresses that we allocate tend to resemble arithmetic progressions, especially if we manage to allocate lots of keys on this 32 kilobyte page. And especially if the alignment, power of 2 alignment of keys is constant. So pointer shifts is an optimistic construction of time. No? 15? Okay. So pointer shift is an optimistic construction. It treats keys as if they formed arithmetic progressions. So it basically first line shifts out the constant low bits and then does a half-hearted attempt to mix in the address of the page, the allocation page. So brings some high bits down. That's all it does. 2 assembly instructions for shifts and 1 plus. So you cannot really get much simpler than that, although I tried. And yeah, but this is so aggressive, it obviously needs some safety net to catch it, which I described. So we switch to prefuzz if this starts to pile up the number of the collisions. So as we see as prefuzz, simplified here, looks like this. It does similar things. It shifts out certain low bits that are likely constant and tries to bring in some high bits. But it's really bad for certain cases, as we have seen, and it is also a good trade-off in practice, evidenced by the fact that this has been in use for like 20 years. Still, the worst case behavior is terrible, so it needs murmur as a safety net. Now, if we put this into practice and measure, replace SBCL's hash tables, EQ hash tables with this, we go back to the previous 3 examples. First, existing symbols as keys, not much structure in the data. They are all over the place, not allocated in a tight loop wherever they are. Regret is pretty much the same. Now the red line doesn't extend to the left because it starts out with the constant hash. That's not really a hash table like the linear search part. I'm not plotting that. Now you can see that this phase is much faster for insertions and not a whole different for lookups. But what's not plotted here is the GC impact, which is huge. Anyway, there is a 2% improvement due to adaptive hashing, pointer shift being faster and simpler and faster than prefuzz. Not really visible on the log scale that I use here. Right? For arithmetic progressions of fixed nums, being the keys, now adaptive is a zero regret perfect hash. Does that translate into performance improvement on insertions? Not really. Like in the constant hash phase, yes. After that, no, because prefuzz is terrible, but it gets away with it because collisions are between neighboring keys. So it doesn't have to pay the price on current CPUs. For get, on the other hand, we get a 50% improvement in lookup speed because those collisions for prefuzz do matter. So we have 2 things going for us: faster hash function, similarly, well, zero regret, and that's about it. So that's a large improvement. Back to the single float failure case of prefuzz. Adaptive starts out really well, detects all the constant low bits in the single floats, shifts them out, starts as a kind of perfect hash. But as we add more and more keys, the initial guess as to the number of constant low bits becomes bad, and we do it only once. for performance reasons. So it started to degenerate in performance. It realizes maybe exceeding the bucket limit, maybe at rehash time, it realizes, oh, things are looking bad. I will switch to prefuzz now, which is a really bad idea because prefuzz is terrible, and then immediately switches to murmur. So it improves on murmur, even a murmur at the beginning, and then just gracefully falls back to that performance level. Right. So I could stop here, but I won't. But you can tune out here basically because that's the whole story. We got a more aggressive, faster, handcrafted hash function, basically, that is as robust as a uniform hash. And that's the gist of it. We can pull something like this off for equal hashing, but here we only speed up the hash function itself. We don't care about regret or cache friendliness because that's hard. So what we do is we hash only the first two and the last two characters. It's quite aggressive. And if collisions pile up, we double the limit. Regret stays pretty much the same. And we get 50%, up to 50% improvement up to a certain size for both insertion and lookup. So this is a pretty huge difference there. Now, eventually it falls back to baseline performance because the data used in this benchmark is constructed. There are keys which differ only, long keys which differ only in the middle characters. So eventually the truncational limit will have to increase to beyond the length of most keys, and we basically end up doing hashing normally. So this is expected. Micro benchmarks aside, does this effect actually translate to real life performance? It's not a given, right? Because code is more complex, bigger. Instruction cache pressure is a thing, so anything can happen, and did happen for a long while until I managed to optimize it over the course of 6 months. So I did quite a few macro benchmarks, and in the end I was happy to be able to reproduce the relative gains that I've seen on the micro benchmarks. So all is good. Limitations. All of this is based on using cheap bad proxies for actual performance, for expediency. So we use the collision count and the maximum chain length, which correspond to really loose upper bounds and the lower bounds on the regret. And the regret itself is a terrible proxy, as we have seen, for real-life performance. And this whole scheme is quite hard to implement without introducing too much overhead. It requires, as a handcrafted hash function, it requires understanding the key distribution well. I had to understand the memory allocator a bit to be able to construct a parameterized family pointer shift of hash functions that works well. So our conclusions are general purpose hashing can be improved, of course. Like the big O is not the full story. Normally we don't care about asymptotics that much, and it eats all the constants. Handcrafted hashes are dangerous because we normally don't have fallback, and it's absolutely necessary. Hash functions must be aware of all the keys in the hash table unless we are prepared to give up performance or robustness. And we have shown that hash functions can be adapted online, which is the tricky bit. Yeah, it's possible to pull this off. It just takes a long time of low-level hacking. And maybe most importantly, that the design space that opens up is large. So the actual hash functions that I showed in this presentation are not particularly interesting or inspired, but they do demonstrate the basic idea, which is bring stuff from perfect hashing into the online realm and try to claw back the performance that we have given up or theory has given up for us already. So finally, I would like to thank all the people who provided valuable comments on the manuscript. Code is not yet merged, and paper is available. Thank you. Yep.
So I misspoke. We're actually just like 10 minutes late, so we're aiming for 12:40. So 5 minutes. Okay, so questions.
Second microphone. Oh, okay. Well, whatever.
If I understand your cost function correctly, you are not interested in negative lookouts. Is that correct?
The paper has the data for that. I'm interested in that, but the actual cost function. So I pay lip service to theory just to present it and contrast it with reality, but the theoretical cost function bleeds from several wounds, and this being like one of them, it does not include the negative lookouts.
Do your micro benchmarks or the macro benchmarks, of course, but the micro benchmarks, do they include keys that don't exist?
Yeah. So yeah, I just didn't present all the figures.
Any other questions?
Does adding concurrency add anything interesting?
Adding concurrency, yeah.
So using writing and reading the hash table from multiple threads.
Well, it's a complication that I can, of course, see, but yeah. So this was done in SBCL hash tables, which just lock if there are multiple readers, writers. I didn't really think about whether performance-wise I can get anything out of multiple threads. The idea was to keep the implementation as close to as possible to the existing one and just focus on the basic idea. Yeah, I can probably hide under certain circumstances more of the cost if I have multiple threads, but that would be something that people would object to in general in a hash, would be unexpected in a general purpose hash table implementation.
I was more thinking about place locality in a single thread is great.
Okay.
It may be bad if multiple threads want the same cache line.
Yes, and different workloads as well. The micro benchmark stories would not hold if I had different workloads which put more pressure on the memory subsystem. Yes, true.
Okay.
So I don't think I really understood the macro bench. So you're saying you tried the macro benchmarks and you didn't see anything significant because the macro benchmarks you used weren't even hashed.
So yeah, all right. I just rushed through this. So I estimated the time spent. How many percent of the time is spent in hash table operations for each of these? It was like 2 to 4. And out of that 4%, there is a gain of like 0 to 50%, depending on the actual hash table and the workload, relatively. So overall, out of the 100%, that would constitute 0 to 2% gain. And that's what I meant. It survives the transition to the more complex workload. You get the same relative gain, so basically as on micro benchmarks, but it's much harder to estimate. And if you heard my benchmarking talk at SBCL 25, this is the reason. It's really hard to estimate these things.
So what is the aftermath? Because the motivation was you said something about C++ programmers in the beginning.
Yeah, so it's
good enough for what you set out to do. Would you want to upstream make this work?
Yeah, I want to have the discussion what to upstream out of this. immediate motivation for me is to demonstrate that this is possible, and I don't really believe that I can convince C++ people to like go and implement this, but that was the original idea. I thought I would spend 1 month of my life implementing this, and that was last September. Yeah, I did 1 month at least.
Okay, I think this is it. So thank you very much.
Thank you.